Welcome to Lesson 9 of Electromagnetism for Teachers. Last lesson we looked at properties of light and in particular polarization. This week we're looking at interference of light, beginning with one of the most important experiments of all time, Young's double-slit experiment. For the rest of our course we are dealing with wave optics, which describes behaviors of light that cannot be explained by geometric optics. We've already done polarization. This lesson covers interference, and our final lesson is about diffraction. So we'll begin our lesson on interference by talking about the experiment that began the investigation of the wave property of light, and that is Young's double-slit experiment. Since light is a wave, it obeys the principle of linear superposition that you have already learnt about when studying waves and in particular sound waves earlier. So the principle of superposition is that the resultant of any number of overlapping waves is the sum of the disturbance due to each wave. Interference is the cause of iridescence, which you can see on this butterfly and in the feathers of this purple-crested turrico. It means that the object gradually changes colour as the angle of view or the angle of illumination changes. Later we'll be looking at why that happens. You have encountered interference before, so we're really only interested in two cases. Firstly, when the two waves are in phase. So this means that their peaks are reaching the screen at the same time, and so are their troughs. What we see on the screen is double amplitude peaks and troughs. So if this is what is reaching the screen, this would make a bright patch, and this is what we call constructive interference. When two waves are 180 degrees or pi radians out of phase, a peak from one coincides with a trough from the other, and the two cancel out. This is called destructive interference, and this is what we see as a dark patch on the screen. Young's double-slit experiment is the one that proved that light is a wave, but understanding that experiment requires us to know the concept of diffraction that we've already spoken about. That means that light passing through an opening in a barrier will flare outwards or spread out into the region beyond the barrier. The wave fronts here that you can see from the water are actually curling around the edges of the aperture. You see here a plane wave encountering three different widths of slit. The wave spreads out the most after the narrowest slit. This explains why we don't see diffraction of light round everyday objects. They are so much larger than the wavelength of light that the amount of diffraction is negligible. You need tiny thin slits or pinholes to see diffraction happen. Notice that in this diagram the slit at the top has a width of 6 times the wavelength, and the light really isn't spreading out all that much. In Young's experiment, a plane wave hits a single slit and diffracts outwards as if that slit S0 was a point source. Then that light hits two narrow slits. The light diffracts from each slit and forms an interference pattern on the screen over on the right-hand side. So the slits S1 and S2 are acting as two point sources of light waves. And the waves leaving the point sources are in phase. That's because they're an equal distance away from S0, and so the wave fronts will be reaching them at the same time. So that means from S1 and S2, two crests leave at the same time and two troughs will leave at the same time. Remember, we're talking about crests and troughs in the electric and magnetic fields. So the two waves that are in phase at S1 and S2 overlap on the screen, and they form an interference pattern. What you see is a series of light and dark patches on the screen. These are called fringes. The bright parts are where constructive interference is happening, and the dark bands are where the interference is destructive.